Jean-Sébastien Filot. He is substituting for his colleague Marie-Liesse Doublet, who cannot attend today. So thank you very much for jumping in on such short notice. And we're looking forward to your talk entitled Electrolyte Stability and Reactivity in Magnesium Batteries. The floor is yours.
Okay, thank you very much for the invitation first. And I want also to say that my colleague Marie-Liesse Doublet is very sad not to being able to assist to this very nice meeting. So now I'm going to switch to some kind of theory. And if you have any question, don't hesitate to contact me through my email. First, I'm a theoretician of interface electrochemistry, and as any interface electrochemistry is quite complex because you have to both compute the active materials, the double layer, and the electrolyte. And because of that, there's a lot of complexity, and one of the main complexities that is appearing in this kind of interfaces is the presence of surface charge and very strong electric fields that are going to change completely the chemistry of the system. So, of course, this kind of interface are very important because they are directly part of degradation, SCI processes. For safety, they are directly linked with dendritic growth. And, of course, for all the batteries characteristics such as power and efficiency, they are directly linked with the electrochemical kinetics and catalysis that can occur at this point. So they are very important really to understand, and theory is really the tools to look at, to have a look at this position. So first, there are many existing models to really try to understand what is happening on the electrochemical interface. The first one is, of course, you can use extract from the Nernst equations, where mostly, if you do that, as the Nernst equation is done for uncharged system, we model system with interface with no charge. It's mostly what was developed for electrocatalysis by Noskov. But these things can work very well, but sometimes it can bring some issue. As an example, I'm going to talk about the simplest system, that is the lithium reduction and formation of nanocrystallites. As you see the shape of the nanocrystallites, if you compare them to what you get if you only use the surface energy you get from DFT calculation, you get very, very different structure. So you see that the classical approach that is using zero charge can be very wrong to getting proper energetics for the interfaces. So what you need is to get into more complex modeling that should include the surface charge, of course, the electric field, and eventually explicit and implicit solventation of your interface. In this case, you get some kind of equivalent Nernst equation that will depend on the local electric field. That is not practical. So to be practical, we are using the free electrochemical energy. That will be our main energetics. And it works both for adsorb molecule on the surface, but also molecule in the double layer. So it allows investigating a wide range of very different behavior in electrochemistry and answer both questions and reactions happening on the surface or really in the double layer. This approach, what are we doing? Mostly we are computing a charged surface. Of course, if we are going to compute an uncharged surface, that is mostly the classical approximation, but we are going to get other charge system. We are going to charge our surface, and we are going to have more and more, for example, oxidized system that will get different potentials that we are going to compute, and we can also get the reduced system. From this simple approach, we get the free electrochemical energy that is presented there, and that is mostly an inverted parabola shape. With at the bottom of it, you will get the potential of the zero charge, and the curvature of it will be proportional to the surface capacitance. Then we already get some very specifics of surface and interfacial electrochemistry. So if I redo that for the last time to lithium, what I get is, if I look to the uncharged system, in fact, I get that the uncharged system for lithium is associated with a potential of plus 1.4 volt relatively to lithium. So in fact, when you are modeling uncharged lithium surface, you are modeling unstable system, because at 1.4 volts, the stable form of lithium is not metal lithium, it would be lithium plus. So you are computing a system that is not possibly experimental. So to get to really negatively charged system going to zero relatively to lithium, we can get a charged system, and we find that we get completely different surface. When it's uncharged, it's a 1,0,0 surface that dominates energetics, and when it's under reduction, under negative potential, it's a 1,1,0 surface. And in this case, you see that we are able to reproduce the shape of lithium particle. So it's one thing to say that charged surfaces are really important to really get proper surface and interface energetics. So next, in my little tutorial, how do we model electrochemical reactions at an interface? In fact, we need a redox pair. We have some kinds that will be react as the oxidant, for example, some kind of A plus over the surface. And we will need another interface that will compute, that will be the reduced interface, that will be, in this case, for example, lithium, that will be deposited on the surface. And in this case, when we have computed that, we can extract the electrochemical reaction. When the true free energy curves just cross, we get the equilibrium potential associated with the redox system. We get the redox equation, and we can even get the number of exchange electrons. In this case, that will be close to 1. Not exactly 1, because it's also including the surface polarization that is needed to maintain the potential constant. So below this potential, the reduced lithium metal will be the stable form, and above it will be the lithium plus. So by using this formalism, we are able to investigate the electrochemical reaction on the surfaces or in the double layers. So now I will switch back to magnesium. As the previous speaker just tell about, it's really an interesting material to get some better batteries, but many problems are still to solve. And one of the many problems that were already talked about is the solvent problem and the stability of the solvent at the interface. So we spent some time investigating what is happening with magnesium in this case. So first, we checked that we get the proper energetic for magnesium. So we model the magnesium nanoparticles at different potential. We find that if you do the uncharged surfaces, you will get a very long potential relatively to magnesium, plus 1.6. So it will be, once again, a metastable system. The structure corresponding to the zero charge will be quite similar. It will be mostly an bulky octahedra. And when you go to very high over potential, you get some kind of hexagonal platelets that are system in correspondence what is found experimentally. So things seems to be fine also for magnesium as for lithium. Now, the first step of our study was investigating the simplest reaction, that was the transformation of magnesium 2+ into magnesium metal at the interface. We did a study on the different solicitation spheres, so we find some kind of always octahedra over the magnesium. We did it for two solvents, the classical one used in the classical carbonates used for lithium that we model in this thing that is of course not the best for magnesium, and we are able to get the reduction potential in ethylene carbonates. That will be minus 2.37 versus standard hydrogen electrode. That is very close from the experimental data that is around minus 2.4. If we look at the same reaction, we of course exchange two electrons, and we can also do that with another solvent that will be DME. And with DME, in fact, we get mostly the same thermodynamic properties for the reduction of the magnesium 2 under magnesium 0, that will be also around minus 2.4. So for the moment, everything seems okay. But when we did all this area of experiments, we had some kind of surprise. When we go under too much reductions, we get some kind of instability into both systems. When we go beyond about minus 0.7 relatively to the equilibrium potential, there's a spontaneous reorganization of the solvated cation. That was not observed in previous studies with lithium. So it's really something specific to magnesium in this case. And what we did observe is different behavior depending on the solvent. For DME, we observe a spontaneous decomposition into ethylene and mostly methanolate, magnesium dimethanolate at this potential. So mostly that would correspond to reduction not of the magnesium 2, but of the solvent around it. And for ethylene carbonate, we also observe spontaneous evolution, but that is this time a dimerization. We have two ethylene carbonate molecules that will just form a carbon-carbon bond with many other reorganization in the geometry of the ring. So in this case, we observe that with these different solvents, we have very different chemistry. Could of course be somehow expected. Now, we wanted really to identify the associated process, this time not associated with the reduction of the magnesium, but with the reduction of the solvent molecule that is associated, coordinated to the magnesium atom. And in this case, we look for, to start with the molecule in ethylene carbonate. And what we find, that we find a specific free energy for the new dimer. And then we just try to find the behavior of this dimer under this time oxidation. And what we get to around 0 volts, we get simply the reaction going back to the initial state. So we have some kind of reversibility between two ethylene carbonate coordinated and some kind of dimer. We get, of course, all the potential, the thermodynamic process. We get that the reduction just occurs there, meaning at plus 0.7 versus magnesium, also meaning that the ethylene carbonate is reduced before the magnesium. That can be a problem. And this also occurs for the DME molecule, but this time with fragmentation. And of course, the fragmentation is irreversible. When the fragmentation occurs, there's no turning back because the ethylene molecule cannot find its way back to reform the initial DME. And this also is associated not with the reduction of the magnesium, but a reduction of the DME molecules. So we can already define a stability domain where the solvent is going to be stable, but we have another new domain where the solvents will be only metastable. We can find it, but it's not the most stable species. The one will be either the dimer or the decomposed DME molecules. And anyway, above a limit, there's no stability at all of the undimerized or unfragmented solvent they will just become unstable. So there's a stability limit for these systems. So exactly, how can we understand this instability? Actually, this instability is really specific to the solvents that are coordinated to magnesium. If we do this study with simply ethylene carbonate or DME at the interface, we observe no dimerization, no spontaneous decomposition. You really need to have magnesium that coordinates the solvent. So what is happening? So mostly in the case of free solvent, not coordinated to the magnesium, just in the electrolyte, the Fermi level just is in the electrolyte potential range. The Fermi level of the surface is sitting just between the HOMO and the LUMO of the solvent molecule. So in fact, no electron transfer is possible. There's no reduction that can occur. But when we just coordinate the solvent molecule to magnesium, the effect of magnesium on these molecular orbitals is to shift down all these orbitals. And in particular, the LUMO is going to be shifted down, and it can be shifted down upon the range of reduction of the surface. So because of the attachment to magnesium, some of the attached solvent molecules are going to be reduced and can undergo this reduction that will lead to either dimerization or fragmentation. So one of the problems of the magnesium 2+ is really created some kind of activation of the solvent molecule. It's very close to what is observed in organic chemistry, and it's some kind of electrophilic activation that facilitates the solvent molecules reductions. That, in fact, is really the problem. Solvent alone is stable, but when it's coordinated to magnesium, it becomes sensitive to reduction. Okay, so can we go a bit further on? And we know that we have some metastability, but we want to get more precise, more detailed range of this metastability, because we know that for many solvents, even in their metastability range, it can be used in electrochemistry. In this case, what we looked at is the total charge of our complex with the magnesium and the attached solvent around it. Is first the Rachel shell. And with that, we are going to look at the charge as a function of the potential. What we see is we really got a +2 charge most of the time. And at some point, electron is transferred to the surface toward the solvated Mg2+, and some reduction occurs. And this can give us a first hint where the electrochemistry is going to happen. So it's allowed to give us the electrochemical inactive magnesium 2+. And when electrons start to be transferred, starting to activate the solvent reduction, it gives us the activate reduction, where certainly all the dimerization and fragmentation are going to happen quite fast. So because of that, you see that the blue line is the potential of reduction of magnesium. What we observe is we still have a very small zone, about 100 millivolts, where we can get an electrochemically inactive magnesium in DME. But this electrochemically inactive DME will start to go quickly in the reduced activate zone. So we are going to reduce both magnesium and the solvent. For ethylene carbonate, it's about the same, but ethylene carbonate should be quite better. The electro-inactive zone is slightly larger around magnesium, so ethylene carbonate should be better. But of course, ethylene carbonate is not better, so there's something more to understand. And to really understand, we need to focus on where the reduction just occurred. This can be given by the Fukui function. The Fukui function is some kind of mathematical tool, but that gives you the chemical ID of reduction center. When we compute it, it gives us where the electron flow from the electrode. So when I just add electron to this molecule, I directly see that in the DME case, I'm getting some kind of sigma star system reduction that will lead to CO bond breaking and the formation, you see it there, of some kind of C double bond, and that tells you that's going to the formation of ethylene and methanol. While for the ethylene carbonate, what's going to happen is a reduction of the pi star bond. And we also see that we are going to weaken a lot because we are going to into an interbonding space, the CO bond in the ring. So that means in this case, we are going to favor the dimerization, but we are going also to favor the ring opening in ethylene carbonates. And when we look more closely at the reduction process for DME, we directly see ethylene formation and methanol. And once we get this species, the problem is it cannot be reduced anymore. The methanol presence, when we compute the reduction potential versus magnesium, it's very low. So that means we are creating a mostly inactive material. So the consequence of the solvent reduction in this case is the creation of inactive material, and from the form that's certainly going to precipitate at the electrode. In the second case, in the case of ethylene carbonate, we form the dimer, but what we see is a strong ring opening tendency. And when ethylene carbonates undergo ring openings, it tends to form a polymer. So the problem with ethylene carbonates, it should be a better solvent, but the problem is going to initiate a polymerization reaction at the electrode. That is not a very good idea because it's going to certainly passivate the electrodes. So if we look at the experimental results, I've said there's a magnesium reduction. And what we see, if we look at the zone where our solvents that is coordinated to magnesium start to be unstable, we see that some kind of reduction already happens. That is certainly a mixture of magnesium to reduction, but also of DME, and some kind of precipitation that is going to isolate the electrode, and we see that there's a decrease of the intensity recycling. In the reduction part, we also see that the amount of oxidized magnesium is quite low in comparison to the one that was formed, and we have very low efficiency, meaning that there's some kind of secondary reaction that is happening. In the case of ethylene carbonates, what we observe is, in this case, if I set over there the magnesium 2 plus magnesium reduction process, the potential was the solvent ethylene carbonate is starting to get reduced. We see some kind of decrease in the intensity that probably is linked with the formation of the polymer that start to form and start to passivate the whole electrode and decreasing quickly the intensity to very low values. In the second part, what is interesting also with ethylene carbonate is actually we find a peak at around minus 1.4 that directly correspond to the dimer monomer equilibrium we previously find. So that's certainly one other indirect proof that things are happening with this kind of magnesium. So to summarize this part, mostly what is annoying is DME is not stable enough under reduction and just will break down. And ethylene carbonate could be stable, but the problem is undergoes strong activation and you go to do polymerization and you are passivating your whole electrode by creating something polymer. So good question is, how can we prevent that? One proposition was adding chloride to your electrolyte and to form different kind of magnesium chloride that we compute. But the problem to really investigate your reactivity, you really need to understand the relation between potential and chlorination. So mostly what we need to do is to do a Courbet diagram for this kind of system. So we did it, and mostly we just find the experimental observation with all the different magnesium chloride compounds, more or less complex, that are found. So we are happy, mostly we can find experiments, but the problem actually is that's the bulk electrolyte diagram. But bulk electrolyte diagram is not really interesting to understand the electrochemistry. Because, in fact, what you need is what is happening on the surface. So we need to really build the surface Courbet diagram. And in this case, we see that the Courbet diagram is really changed because of the very strong electric field at the interface. And in this case, the active species at the interface are not the one of the bulk. And then once we have reached to this kind, we can look at the stability of the species. Of course, with pure magnesium, we have observed we have a very low metastability of the DME. It starts to be reduced quite close to the limit of reduction of magnesium 2. But if we use some chloride compounds, the metastability range is strongly increased. And the more we add, the more it is increased. So chloride is certainly a very good thing to improve the electrolyte stability by, in fact, decreasing the electrophilicity of magnesium. But of course, if you add too much chloride, you are going to precipitate MgCl2 and you are going to clog your electrode. So to conclude, here is just the explanation that is Mg2Cl2. And when you look to Mg2Cl2, in fact, Mg2Cl2 you don't undergo any reduction on the DME molecules. So it's really the proof that the chloride has a protective behavior with this kind of system. So to summarize everything, with our approach, we can go to thermodynamic parameters. I've not shown it there, but we can also get kinetic parameters and link with electronic properties. And we can have also ideas on why magnesium is such a pain with the solvent, because it's a strong Lewis acid and it's activating the reduction of it. It's also activating the oxidation of it in some case and changing the chemistry, but I won't talk about that. So thank you very much for your attention, and I'm ready for any question.
Thank you very much for this very detailed analysis and for sharing it with us. We have 5 minutes for questions. Max, do you take over?
Yes, yeah, thank you from my side. This is on the one hand surprising, and it's very, very interesting. I mean, we of course suspect the highly charged or the high charge density of the magnesium, that it does something, but yeah, that it can really lead to decomposition. This is a bit new to me, actually. Do you know whether there is more evidence for this decomposition mechanism? Like, did somebody observe the ethylene that you propose?
For ethylene carbonates, there are some experimental observation of really thick layers of it that were analyzed mostly to be organic. So some kind of ethylene carbonate polymer is coherent with what was observed. And it's certainly really the polymerization of ethylene carbonate with magnesium that doesn't occur with lithium is certainly one of the problems of all the solvents that have ring carbonates. So that's, and for the DME, there are some observation of ethylene production upon cycling. So, really? Of course, the problem with the interface, it's very difficult to really have things that are happening mostly 1 nanometers away from your electrodes.
Mm. If I take that for granted, this mechanism, then this would mean that we would observe more and more ethylene when we get higher and higher magnesium concentrations in the electrolyte, right?
Actually, yes. The problem would be that you are going to precipitate the magnesium OCH3 that's going to decrease your surface area. So you have some kind of something that looks like flat potential. So you have passivation and creation at the same time. So theoretically, yes, it will depend on the precipitation kinetics.
Okay, I see. I don't see more questions at the moment. So if this is the case, I thank you very much for these new insights. I think this is very important. Please say hello to Marie-Liesse and send her our best regards. And with that, I think we have reached the first break of this meeting, right, Christian?
That's right, exactly. So maybe to finish up this first